Okay, we're going to continue our discussion of titrations. So in this video, I want to extend a little bit more. How are we going to use this titration curve? What things can we find out about our weak acid solution? So here's our titration curve. We began with a solution of the weak acid, and I've given it some arbitrary pH, a little above 2. Depends on the acid, depends on the concentration. But I've got initially a solution of the weak acid. I'm going to add a strong base, so I'm going to start to consume my weak acid. And turn my weak acid into the conjugate base. My initial, at this first point, I have almost all just weak acid. And then, of course, I'm going to start to add, I'm going to begin to add hydroxide. I'm going to start to use this up and start to build this up. I'm going to have a buffer in the middle range. Remember, to have a buffer, to have this stable pH, I need significant amounts of a weak acid and conjugate base, or conjugate base and weak acid. So right now, to begin with, I don't have significant amounts of the conjugate base. I have very little. So it's not a buffer yet, but then I get the buffer as soon as I've added some hydroxide. So I begin to add, and then I get to some point where the moles initial equals the moles added, where I've gotten exactly to that point where I've wiped out all my weak acid, turned it into the conjugate base. That's the equivalence point. At this point, this weak acid is effectively gone. I've got the conjugate base. I have a solution of the conjugate base, and this would be my equilibrium at the equivalence point. And of course, so there are two things that we have to calculate and keep track of during titrations. Here I have got my equilibrium situation, which for most of the range is this weak acid equilibrium, and I'm disturbing equilibrium by adding this strong base. So I've got two things to look at: equilibrium of a weak acid, disturbing equilibrium with the strong base, and I've got to kind of keep track of how things are going. When I get halfway, let's say at this point, I track where is my equivalence point, and I say at 40 milliliters I've reached my equivalence point. Of course, we'll be very precise, so we'll say at 40.0 milliliters I've reached that. Let's look at a special place on this curve. What happens when I'm halfway? At 20 milliliters. When I'm at 20 milliliters, so I can, of course, my equivalence point is easy to find. That's where I'm at the middle of my spike. So I'm going to take that back to halfway. What's occurred at halfway there? When I'm halfway there, I'm halfway done of consuming my weak acid. And I've created, half of that has been created a conjugate base. So I have a solution where I have equal concentrations of the weak acid and its conjugate base. If we look at our equilibrium of this acid, so I'm going to take this weak acid equilibrium, and let's write our equilibrium expression for this. As we're concentrating and calculating our changes in pH, let's solve this equilibrium expression for the hydronium ion concentration. So I'm going to switch these around. I've rearranged my equilibrium expression to this. So the concentration of hydronium depends on the Ka for the weak acid multiplied by the concentration of the weak acid over its conjugate base. When I get to this special point, I'm halfway to the equivalence point, the concentration of the weak acid and the conjugate base are equal, these cancel out, that part of the expression becomes 1. I get the concentration of hydronium ion equals Ka. Let's take the negative log of both sides. Negative log of hydronium is the pH. Negative log of the Ka is the pKa. At that point, the pH equals the pKa. So if I have tracked, during my titrations, I've tracked pH along the way, and I say, okay, halfway, what was the pH? And I record that pH. That is the pH that equals the pKa. So at that point, simply by taking 10 to the minus pH, I can find the value of Ka for that acid. So I can find the acid dissociation constant on a titration by simply doing that calculation. And that becomes one way to identify what was that weak acid. Take that point at the halfway to the equivalence point to find Ka. Okay, let's look at another way of looking at it. What else can I find out about this unknown weak acid with a titration? Let's assume I'm going to take a sample of a weak acid. I'm going to mass it out. I'm going to weigh this sample out, and I'm going to take this mass, and I'm going to add some water, and I'm going to make a solution. But what I've done, though, I know exactly how much in mass. Of course, if I don't know what HA is, I don't know how many moles I have, but I know the mass of HA that went in there. The amount of water I add doesn't really matter. I'm going to now do my titration, look at my curve. And find my equivalence point. So what I'll know is, of course, this is the amount of OH minus added. At the equivalence point, the moles of OH added the moles of hydroxide that I've added equals the moles of the weak acid that was initially present. Therefore, by finding this equivalence point, in this way I don't even have to track the pH. I could just put an indicator dye, look for the indicator to change color. There's my equivalence point. As long as I get an indicator that changes in this range, I can just look for a color change, say, oh, that's my point. That's how much. At that volume, I hit the equivalence point. That is the moles of hydroxide. That's how many moles of weak acid were present initially. To find the molar mass of the weak acid, another way to identify a weak acid, if I find the molar mass, if I know the mass of the sample and I know how many moles of the sample, which I just found out by finding the equivalence point, grams per mole, I have the molar mass of my unknown acid. Another way I can identify that weak acid. So we have our two ways. We can plot pH over time, find the halfway point, that will give us the Ka, the pH at that point. Or I can weigh my sample initially, look for the equivalence point, do this calculation to find the molar mass. Let's look at one more thing on the pH curve for this video. And of course, let's look at the particle. What's going on in this solution as I come along? My first particle model, of course, a solution of the weak acid. This would be conjugate base. I got a solution of a weak acid. Most all weak acid with a little bit broken up. When I'm partway through, here at about halfway through, yeah, I've got some weak acid left. I've got some conjugate base. What happened to these hydronium ions? They were turned into water, so I'll just make this a water. So I've got plenty of water in there. but I got a solution, I have a buffer. I've got weak acid, I've got conjugate base in significant numbers in there. What do I have here? I have almost all just the conjugate base. Maybe there might be the smallest amount, less than 1% of the weak acid. So I have a solution of the conjugate base here. What happens when I go past this point? When I go past this point, what have I done? I've taken this weak base solution and I've added more hydroxide. So what I have when I go beyond the equivalence point, what am I doing? I'm just adding excess hydroxide. So I still have the conjugate base, and I now have a strong base. So I have a mixture of a weak base and a strong base. So the pH will keep climbing, and the only reason it levels off is because the pH is a logarithmic function, so that it will just keep going up. And so all I'm doing is I continue past the equivalence point, which we usually don't track too much. Because what do I have? I just keep adding more base, keep adding more strong base.